Well, good morning. This is Miss Dagenford, and we are going to be looking tonight at water potential. And water potential has some familiar concepts, but there's just enough irritatingly complex ones that it can cause students some frustration. However, if we start with what's familiar, it's going to be much more helpful to us. So let's start with that. So we're going to, and by the end of the video, hopefully you first know the definition. You can work with some diagrams and models predicting where the water is going to move, and also be able to even calculate water potential. So water potential is somewhat based on the concentration. So we know that water moves from an area of high concentration to an area of low water concentration. And conversely, that means water moves from an area of low solute concentration to an area of high solute concentration. Now, if we use that as the familiar, now we can just add something new. Water moves from an area of high water potential to a region of low water potential. Now, that also means from the measurements in the units, it moves from an area that is less negative water potential to a region of more negative water potential. So water potential ends up being just one more measurement of the movement of water. Now, this should be familiar to us. Here's a picture, and we're going from pure water, and you'll notice pure water has a water potential of 0, and water potential uses this little trident, psi, as the variable. And so pure water is 0. Dilute solution, here's a water potential of negative 200 kilopascals, and then here's a very concentrated solution, negative 500 kilopascals. And so what they're pretty much indicating is that it's moving to the right. Now, you're familiar with that based on what you know about the concentration. Water moves from an area of high concentration of water to a low concentration of water. But the purpose here is to kind of show you the new way to look at it. And this applies to cell membranes as well. So we have a low concentration of solute over on the left and a high concentration of solute over on the right. And you can see that the water is going to move to the right. Now, it's not as simple as just the concentration. And what you want to look at is this idea that when there is a solute mixing with water, that solute does have some charges. So for instance, if this is a negative charge and a positive charge, so maybe this is sodium and chlorine, salt water, notice that the water molecules are going to clump around those ions. And what this does is it ends up leaving spaces between the solution. And what you want to think is, in this case, this side, the left side, has less tendency to move. And you can think about the fact that water is congregating around those ions. It's not going to move as much. And then over here, water has a higher tendency to move. And so as it's moving more, it's going to move, in this case, to the left, because it's going to fill up those spaces. It's going to move into the area where there's less tendency to move. It's just going to be able to do that. And this works over on the right. This works with polar molecules like glucose. Notice in the picture on the right, the water molecules are attracted to the glucose molecules, and this leaves just more area for the water molecules to move into. So that's what we're kind of getting into. Now, just to apply what we know, that remember what I said is it's going to go from an area of high water potential to an area of low water potential. And then that means from an area less negative to an area more negative. So we can start real quickly applying this. So over on the left, this would be more negative. this would have less water potential, and then conversely this would be less negative, and it would have a higher water potential. Now, how do we figure this out? Now, the equation for water potential is water potential, which is psi, equals pressure potential, the psi, and then the subset is P, and solute potential, S. So let's talk about pressure potential first. So pressure potential is the amount of pressure on the container surrounding the solution. And what you can think about is water is less likely to move in the container if the if the pressure potential is high. So a quick idea of this is if you have an area that has a lot of water, it's going to be pushing back. So you can imagine a quick idea, here's a plant cell, and if the plant cell has lots and lots and lots of water, if it's nicely watered, the water inside the plant in that vacuole is pushing back onto the cell wall. And so even though water might want to come in, it's getting the opposing pressure from inside. So increasing the pressure potential increases the overall water potential. So in plants, for instance, let me zoom in on that a little bit. In plants, the water moving into the plant cell puts pressure on that cell wall. And so increasing the pressure potential increases the water potential. And what you want to think that way is if it's increasing the water potential, it's going to be less likely to move in. So let's take a look at this. So if you just put a cell into distilled water immediately, like right at the moment that you put in, the pressure potential might be 0, and then the solute potential, because there are solutes, is going to be negative. So just for the sake of argument, -2. So the water potential is -2, and this is distilled water, so it's going to move in. But after it absorbs water, notice there's a lot of water coming in and the water starts pressing back. So in this case, the pressure potential is +2, -2. So at this point, it's gone up. And so at that point, water does not tend to want to come in. Now, in an open system like a beaker, the pressure potential is 0 because there's no pressure coming down on it. If we had like a piston and we're pressing down on it, then the pressure potential would be different. But now, because it's an open system, whatever pressure is put on it can just rise up into the beaker. So it's a pressure potential of 0. In a closed system, that's when we start seeing a pressure potential being influential. It can be a positive number, a negative number, or a 0. Now, solute potential is I think actually a little bit easier, because as soon as you add solutes, as soon as you add any solutes, it makes it more negative. It lowers the solute potential, so it's less likely to move, and that means the overall water potential decreases. So keep in mind, water moves to an area of low water potential. So more solutes means it's more negative. And remember, that means it's a higher concentration of solutes, low concentration of water. So you might remember, if we were to look at this example, that because this is pure water and this has a lower concentration of water, water is going to move in. But if we add our water potential to the equation, over here in the pure water is 0 water potential, and because we have some solutes, it's going to be a negative number. And remember, it's going to go from an area of high to low. And in this case, water is going to enter that side, and we'd see water coming in. So we're just adding some complexity to things that we already kind of know about. Now, the units for water potential is going to be kind of a measure of pressure. It's going to be megapascals, or you saw in the other picture, kilopascals. One atmospheric pressure would be for just good old pure distilled water. So you're kind of seeing the pressure that's being put on it. So let's take some practice problems. Over here on the left, this is the initial condition, cellular and environmental. So the solution is a zero point 0.4 molar sucrose solution, and it's in the beaker, so pressure potential is 0. Solute is negative 0.9, so that means overall the water potential is negative 0.9. Now, the surrounding solution, um, the in the plant is negative 0.7. So think about what's going to happen. It's a more concentrated solution, and notice the water. So this is negative 0.7. It's moving from a less negative to a more negative. This is going from a high water potential to a low water potential. So you can really just look at the numbers and kind of understand, okay, we're going to look for that more negative number. Over here with pure water, and that's going to be 0 megapascals. And then again, the cell is going to be initially negative 0.7. And so notice that means we're going from 0 to negative 0.7 initially. And then what's going to happen is because eventually the water that's come in is going to push back. Think like a big water balloon that's gaining water. That water pushes back on the cell wall. So notice we're going to have a positive pressure potential, and the solute potential is negative 0.7. That goes down to 0. So really that means water can no longer move into that cell. It's just, it can't. The water is pushing back. Now, just to give you a couple more practice, water flows, again, regions of high water potential. So we already saw this example. Water is going to the right. However, now imagine we're putting pressure from above with this little piston. This is a positive pressure. And if we do it correctly, theoretically, what we're going to do is cancel it out, 0.23 and negative 0.23. And again, we're getting at 0. So in other words, the water can't move. The water is going to want to move, quote unquote, want to move here, but the pressure is fighting back. And so it's going to cancel it out. If we increase the pressure, so it overcomes that, notice the pressure is now at 0.3. Now notice the water potential is 0.07. That's positive, and we're going to drive the water back. And so therefore that other one goes high. So again, just look at the numbers. Now we're at 0.07. And this was 0. And so notice this is higher, this is lower, so it's going to go to the left. And then you can also create a tension. Now a tension is pulling, and that means it's going to be negative. You're pulling up on the water, and that causes the solution to want to come up. So in this case, it's kind of tricky at first, but you got to remember that because this is a tension, it's going to be a negative pressure potential. So over here, this is going to be negative 0.30. Over here, this is negative 0.23. And so just looking at the numbers, it's going to go into the more negative direction. Now, this is going to be kind of interesting because trees kind of employ this idea of tension pulling. So I'm gonna leave you with a couple of questions to ponder, and just remember you're going from a high water potential to a low water potential, less negative to more negative. So there's one question. Which of the following statements is true for the diagram? And then here's the next 3 questions. Thank you.